Okie dokie. Hopefully this is working, and I am going to give a very brief slideshow and talk about chemistry. So, teaching how to make slides is not hard. Have fun. It's part of expressing yourself. That's part of what I like about chemistry. Chemistry actually is the stuff of life. So for me, expressing myself and looking around, all around us, sky, stars, everything, reminds me of chemistry and that we are made of atoms. Gravity and even the concept of mass is part of chemistry, and when you look at an atom, that's what's in front of you. And those, to me, give weight, importance even to our feelings and to what's our mind. Our mind is made of atoms, and that's what allows you to think. And we can model and understand those atoms that are us, that are the world all around us, and the world that we can see way out into space. So, atoms and light go together. Atoms are made out of charge, So, part of atomic theory is that the nucleus is made out of a positively charged, super, super dense something, quantum particles. And then around them are these charged electrons that are flying around it. And, something that really exciting happened in the 20th century was discovery and the invention of all of this phenomena, right? I mean, Einstein's miracle year in 1905 is when he first was able to account for the behavior of the photoelectric effect and how photons and electrons work together and, refined the atomic model. By 1932, there was the invention of the first electron microscope by Ruska and others, and they could actually image and understand electrons to make them into a gun and shine them onto a sample and resolve about a micrometer resolution, which was small at the time, but not really compared to an optical microscope. But at the time, they were like, no, this is exciting. And within, 6 years, there was a commercial transmission electron microscope available. And just in a few years after that, by 1945, they were able to make a thin foil of material, shoot electrons through it, and make a transmission electron microscope that enabled unprecedented resolution compared to photons or least visible photons. So 10 nanometers was achieved way back in 1949, 1945. By 1955, the resolution was on a march, and Feynman came in with the Palladium room at the bottom talk and said, we need better electron microscopes. Miniaturization is fundamental. This is how the world is going to be built. This is nanotechnology, and this really locked in with quantum theory and understanding, and we could push the resolution further. By 1975, they could resolve 200 picometers. This is 2 angstrom resolution back in the 70s, right? And a lot of new innovative techniques were developed to understand the spectra. How does the energy distribution of the electrons that are going through the sample, or the photons that are produced by those high energy electrons hitting the wafer, right? So then, we got X-rays and all of the science of how integrated circuits work. And by then, integrated circuits were 5 micrometers, right? So they're 5,000 nanometers in size. There's this huge gap between the resolution potential of the microscope and the integrated circuits that were being fabricated. But we didn't stop, right? It was just the triggering of Moore's law. And since then, now, all the way now in 2017, we're making 10 nanometer devices, right? So these are incredibly microscopic, just unfathomably small pieces of silicon and other materials that enable electric control over the semiconductor properties and ultimately the circuits that we produce to enable these computing machines and cameras and everything you see that's in a smartphone and the servers and self-driving cars, etc. So, but the electron microscope has kind of plateaued at the atomic scale. They can't really get a lot better than that. We're making better electron microscopes, but there's a real resolution limit of the atom itself, and going subatomic is a totally different art form and science, but it's not part of this story. So, at this resolution now of maybe 50 picometers, that's an incredibly high resolution electron microscope that can resolve 2 very closely spaced ionic atoms inside of a molecule. So really this understanding that we have of atomic theory and photons, light, and electrons all goes together. And if you really understand it well and you can explain it simply, then you are ready to teach. And you can flip the classroom yourself. And the better you can explain yourself and understand and simply explain, the more people that you can teach. So measuring it and thinking about it gives you a shot at really understanding it better. So doing more science and understanding something, it gives you a really exciting opportunity. So try it. Measure a piece of paper. Just take a piece of paper and measure the area of it and show your work and just figure it out. Watch this video about the same problem. He was teaching physics, and I think this is a really exciting time. So flipping the classroom benefits all. Right, so there's this little clip. What's the area of this sheet of paper? Use metric units, show your work, think about it. I recently gave a talk at my work where I was talking about the collaboration speed in communication and how important that was. So if you could, check in and test and communicate with others what you're about to do, what you're doing, what you plan, what you did recently and what you plan to do, then you can flip the classroom. You can spend that collaboration time in a way that's going to be functional and useful for everybody. So goal agreement and follow-up is settled via email, but also by shared documents in the tests and the models themselves. The idea is the conception is going to become a model, and that enables measure, model, map, the way of thinking about the world in a scientific way that brings things into focus, right? And that brings me to spectroscopy and rainbows. So when I think about the periodic table of elements and all the elements and electrons and how they interact with charge and matter, then I think of spectra. How does the light coming through those materials affect the absorption and the interaction of the electrons? And there's all this behavior that really gives you this real vibrant gift of understanding the periodic table well, and how photons and light and matter exist, and be able to measure things at unprecedented resolution. So this brings us to chemistry, and I'm going to read a little bit of a chemistry book here, but there's a lot of highlights in chemistry, whether it's organic chemistry or inorganic chemistry, which is the stuff of all the atoms of the periodic table and how they interact and make crystals and really beautiful things, and of course biochemistry, which is what we're made out of, nitrogen and carbon, and the chemistry of organics. It's just so exciting to really understand the way that the body works at an atomic level and understand it well. It's exciting, and the forensic DNA technology, etc., is just layers and layers on top of that. So you've got physical chemistry, quantum chemistry, quantum mechanics, and light. And this combination is just so exciting to me. So with that, I'm going to switch over out of slideshow mode and see if we can make the video work, and maybe start recording the video part after I pause and check my audio. But thank you all so much.